Okay, welcome everyone to the 38th, I believe, 38th meeting of New Directions in Group 3 Triangulated Categories. Today our speaker is Martin Frankland from the University of Regina, and he'll be talking to us about on Goodmorphisms of exact triangles.
Thank you. First of all, I'd like to thank Verdi for the opportunity to speak. It's a great pleasure to be with you all today. The project I'll be describing is all joint with Dan Christensen. And in fact, if you want more details, you can find them in the paper of the same title in the Journal of Pure and Applied Algebra. And I want to start with some motivation. The actual project starts in section 2, but I want to talk about the atom spectral sequence in triangulated categories, because that's what got us thinking about those questions. And it's also a nice story that I want to advertise to all users of triangulated categories, so not just topologists. Well, let's start with topology. The classical atom spectral sequence is a computational device that computes homotopy classes of maps between spectra. Let's say you want to compute maps from X to Y, and then you start with cohomological information, namely some X groups over the cohomology, operations, the C0 algebra, and that converges to homotopy classes of maps. For instance, if X and Y are just a sphere spectrum, this is computing the P primary part of the stable homotopy groups of spheres from the cohomology of the C0 algebra. And in fact, you can use a different cohomology theory to get the E-based atom spectral sequence, the MU-based or BP-based atom spectral sequence. The Adams-Novikov spectral sequence is a popular choice for that cohomology theory. And again, it starts from some homological information, computes some homotopical information. Great, but this is a talk involving triangulated categories. So where do triangulated categories come into play? Well, the original construction was in the stable homotopy category, but in the 60s already, Brinkmann wrote a paper describing how this works in a triangulated category because all the machinery is available. And then this was used in particular by Frankland, who was using, well, okay, his paper was rooted in work of Bousfield. Bousfield classified K local spectra, where K is a periodic complex K theory, or KU, let's say we complete at some prime P. And Bousfield's work was based on the following fact. Well, if you want to compute the homotopy of a K local spectrum, you can use the E1-based atom spectral sequence, and there's only room for a D2 differential. And then he showed that the D2 classifies the K local spectrum you're studying up to weak equivalence. And so the atom spectral sequence played a crucial role in that story. And then Frankland tried to generalize that to other triangulated categories where there's an atom spectral sequence with similar behavior, where you can then try to compare your triangulated category to some kind of derived category of comodules or some kind of algebraic model. And then Frankland's construction was further refined and extended by Leutzheim, Barnes, Pachkoria, and various authors to study various localizations of the stable homotopy category or some module over various ring spectra. And that's all still in topology, but it turns out that you can apply the triangulated atom spectral sequence to other more algebraic setups. For instance, Dan used the triangulated atom spectral sequence to compute things about stable module categories, certain ghost lengths, and other related computations. And there are more examples that are more algebraic in nature. So if we have this triangulated atom spectral sequence, well, what kinds of setups do we want to use it in? Well, the motivational or original setup was the stable homotopy category. But again, I want to invite also non-topologists to think about those things. So you might want to think of the derived category of a ring or a more general derived category of an abelian category. And perhaps you like stable module categories of group algebras or more general Frobenius rings, all kinds of triangulated categories out there that we can use as playground to apply some atom spectral sequences. But for that, I need to tell you, well, what resolution is allowed. And to prescribe certain kinds of resolutions, you need some relative homological algebra. That's what relative homological algebra is about. It's about varying the kinds of resolutions you're allowing. And that goes back to work of Eilenberg and Moore, who gave some framework for relative homological algebra. And in a triangulated category, that gives you the notion of a projective class. And a projective class is saying, well, what are the fake projective objects and what are the fake epimorphisms? Or by taking the cofiber, the null maps. And they're related to each other as follows. This class P of fake projective objects are exactly those that think that the null maps are actually zero in the sense written there. And conversely, the null maps are exactly the maps that look like they're zero from the point of view of the fake projectives. And so the two classes determine each other that way. And to build resolutions, well, you need this axiom that says that any object admits a P epimorphism from a P projective. Or equivalently, the next map is null. And this is the third axiom there. And an injective class is defined dually. And how is that related to the atom spectral sequence? Well, let's see. Let's look at a few examples. If you take the projective class generated by spheres, and they're suspensions, so spheres of all dimensions, then, well, you're forced to allow all wedges and retracts, just formally. And the null maps are those inducing zero and homotopy groups. That's the ghost projective class. And if you take a spectrum, E, and you take shifts of E and products and retracts, then you end up with an injective class whose null maps are those inducing zero on E cohomology. And in fact, that is the classical example where E was just HFP, the mod P Eilenberg-MacLane spectrum. That gives you the cohomological atom spectral sequence. But the atom spectral sequence is more useful if you turn it into the homological version often. So you want that as well. And it's also an example that fits into that framework. You take your favorite ring spectrum, nice ring spectrum E, and then your injective objects are the retracts of E smash some other spectrum. And the null maps are those that become null after smashing with E, which is stronger than inducing zero on E homology. It's a stronger condition, and those are the null maps. And this injective class gives you the E-based homological atom spectral sequence. So all those classical variations all fit into that picture. And it's convenient to have a stable projective class, which is closed under suspension and desuspension. All right, you don't have to. You could, in principle, not require that. And let's look at some more algebraic examples. If you work in DG modules over a DG algebra, differential graded algebra, then you can play the same game that we did with the spheres, but now you take just shifts of A itself. And there are sums and retracts. And then the null maps are those inducing zero on homology, and that gives you the ghost projective class. So the algebraic cousin of the ghost projective class we had in topology, where homology now plays the role of homotopy before. And the atom spectral sequence here gives you a familiar spectral sequence, this universal coefficient spectral sequence. And I know some of you like your triangulated categories to be tensor triangulated. So if you have a nice tensor product, you can also compute this Eilenberg-Moore spectral sequence, or you can recover the spectral sequence as an instance of that construction. And there are many more examples, but I wanted to give a flavor of what you can do with those things. Now, what's the construction? Well, you start with your target object Y, and you want to resolve it. Well, what's the resolution? If you go back to classical topology, what's going on here? So this I0, think of it as a product of Eilenberg-MacLane spectra, and the P0 is going to be a map inducing a surjection on cohomology. And then you take the fiber, and you repeat the process. The P1 to I1. Oh, actually, I don't know why I'm just I'm just gesturing in front of the camera. I have a cursor to do that. There we go. So this P1 right here, think of it as a map to a product of Einberg-MacLane spectra, inducing a surjectional cohomology. And you take the fiber and then repeat that process. Oh, those arrows with a circle on them mean that means that they're shifting degree by 1. That really maps into the suspension of what you see in the target. But it's convenient to close up the triangle instead of unwinding it with more and more suspensions. So yeah, that's the circle here. And once you have that, then you can map. Oh, right. And you can form that resolution precisely because of that third axiom in the definition of projective class. And then you map out of the other spectrum X, you get an exact couple and a spectral sequence. That's the Adams spectral sequence. Great. So it's all available in that setup of a nice triangulated category with a projective class or injective class. And it starts with those I relative X groups. And depending on your injective class or projective class, those might be horribly complicated or fairly simple. There's usually a trade-off. The Adams spectral sequence will be more powerful if you can see more information, but then you get more complicated X groups. So yeah, there's always this kind of trade-off. Or according to the Mahowald principle, right? If you have an algebraic E2 term that computes the stable homotopic groups of spheres, then your spectral sequence must be infinitely far from the actual answer. So that's how life is. Now let's do a bit of philosophy for a second. I'm guessing that in this audience, there's some sympathy for triangulated categories, but in the homotopy theory community, that is a controversial issue. So let me address it head on. Why would I work in a triangulated category instead of, say, a stable infinity category, or maybe a stable model category that covers most examples arising in nature? So let me give you a few reasons you might want to do that. Well, you're assuming less. You have fewer hypotheses. If what you're doing relies on couple equations in the triangulated category, why assume a whole package of a billion equations in the background that you're not using? So, just stick to what you need. And it's just surprising how much you can do with the triangulated structure only. The Adams spectral sequence is an example, and higher total brackets, something we worked on. Neeman's work on the K-theory of triangulated categories, I think, is a wonderful example showing that you can do a lot without assuming some enhancement. So yeah, we just want to see how far you can push that without assuming some model in the background. And also anything you construct just using the triangulated structure by nature is a derived invariant. It does not depend on a choice of model or a DG enhancement. So you don't run into issues of rigidity or uniqueness of enhancement. Or conversely, if you're interested in questions of uniqueness of enhancements, well, knowing that something is built just using the triangulated structure tells you that it's useless to distinguish different enhancements. So it can still be useful. All right, enough philosophy. Now let's go back to Adams resolutions. In what we were looking at, we were dealing with some Adams resolution, and then we were looking at some induced maps on some cofibers, but we didn't want to just pick them at random. We wanted them to be as compatible with each other as one might hope. And we're wondering, well, how compatible can those be? So how convenient can all those choices be made? Which led us to the actual project that I want to present. So answering this question led us into the side project, which became its own thing. So now we switch gears and try to answer that question. Let me recall some work of Amnon Neeman on Goodmorphisms. He proposed this definition. You start with triangles in some triangulated category. I'm a topologist, so I denote my suspension functor with a sigma. But if you're an algebraicist and you prefer brackets 1 for the suspension, that's also fine. This is an inclusive space. And if you have a map of triangles, just a diagram of that shape, you can look at its mapping cone, which is defined just as in good old-fashioned homological algebra as the mapping cone of a chain map. Well, except that it doesn't go on forever. It's wrapped around because, yeah, it's a triangle. And this is the formula. It's a mapping cone. And if that is still a distinguished triangle, or exact triangle, in today's talk, yeah, when I say exact triangle, I do mean the same as distinguished triangle. I think some papers by May use exact in a slightly weaker form, some kind of homological or Yoneda exactness. Today, I mean the same thing, just distinguished. Right, the map is called good if its mapping cone is an exact triangle. All right, what can we say about those good morphisms? Well, for one thing, if you start with a good morphism, you can extend it to a 4x4 diagram. And that might be reminiscent of work of Verdi in the, I think it was in the 60s, early work on triangulated categories, where he showed that any square you start with extends to a 4x4 diagram. But you see that now we're starting with the whole first two rows, the top rows. And that's why it's not always possible. But if it is possible, we will say that the map of triangles was middling good. Yeah, so Neeman was saying that if you start with a good map, you can definitely extend it to a 4x4 diagram. But that is in fact a weaker condition that Neeman calls middling good. All right. And there's a related notion, going back to Verdi's proof of this 4x4 lemma. If you look at his proof, it uses a specific construction to build a 4x4 diagram. And we will call a map Verdi good if it is constructed as in Verdi's proof of the 4x4 lemma. Now, okay, that's not a complete definition if I don't tell you how that goes. So what was Verdi's proof? Well, first he used an octahedron based on the first two maps here, so right and down, and then you pick an octahedron based on those two maps, and then you do the same thing with the other composite, so down and right, pick an octahedron, that's going to give you this second step, and then you compose. So the first octahedron was giving you the first step, the second octahedron gives you the second step, you can compose them. This new intermediate object that appears, think of it as the cofiber of the diagonal map of the original square you started with. So these two equal composites have a cofiber, and that's this object A. All right, and by Verdi's argument, we're saying that if a map is Verdi good, then it is middling good. It can be extended to a 4x4 diagram. That's the reason that he introduced this construction. And it was pointed out to us by Haynes Miller that you can algebraicize this condition. Map is Verdi good if and only if it extends to a 4x4 diagram and it satisfies a few more equations. So we can explicitly write down the additional equations. No need to try to remember all of that by heart. The point is just that you can write down a list of equations that give you Verdi goodness. So it's given by those three diagrams here. Oh, and my -1 here means anti-commutative. Yeah. So keeping track of signs in this whole business is about 50% of the work. It can become a nightmare sometimes, but yeah, there are signs everywhere. All right. What are some examples, non-examples? Well, Neeman observed that if you have only one non-zero component, then the map will be good if and only if you can factor this H as a composite going right, then 2 steps back and down, and then to the right again. So let me draw that on the diagram. That kind of factorization, we call that a lightning flash because it has that shape. And those are the good maps. And in fact, this is also equivalent to Verdi goodness and middling goodness and some condition involving the total bracket So the total bracket of what three maps? Those three maps, this little snake here, has some non-empty total bracket because each of the twofold composites are 0. And if it contains 0, then you're looking at a good map, and conversely. All right, so that's nice. For simple enough maps, we can characterize what's going on, but then it gets trickier for more general maps. And yeah, the same is true for if you put the non-zero component elsewhere. Now, this might look obvious because goodness is invariant under rotation of triangles, but Verdi goodness is not. There's this asymmetry where the third map H is really the one that you factor in a specific way. And based on that characterization, already we can produce some small examples or non-examples. This map in the derived category of abelian groups is not middling good. I mean, you can also check that explicitly if you try to write down a 4x4 diagram, it just doesn't work. But you can use the previous characterization. Or if you play the same game in stable homotopy theory, if you take more spectrum and you look at this map of cofiber sequences, well, it's not middling good for the same reason. All right, so already not all maps of triangles are middling good. And what else can we say? Well, here's a useful tool. We say that a map of triangles is null homotopic if it can be written this way. So again, it's the same formula that you learn in homological algebra with chain complexes, but you just have to be careful because unlike chain complexes, now those wrap around after 3 steps. And those are the formulas you need. So you don't introduce signs here. You shift as needed, but don't introduce signs. And 2 maps are chain homotopic if their difference is null homotopic. So far, it's very similar to what we do with chain complexes, but just wrapped around in a 3-periodic way. Well, if you have chain homotopic maps, their mapping cones are isomorphic. So not just quasi-isomorphic or something. They're actually isomorphic as objects in the triangulated category. So right away, you know that goodness is invariant under chain homotopy, right? Because being exact, being a distinguished triangle, that's closed under isomorphism. But we would like Verdi goodness to also satisfy that, and it's not clear. It's certainly not clear from the definition. There are certain cases where that is known. For instance, Neeman observed that if you change that third component H, you just add a lightning flash to it, that's a special case of chain homotopy, it's of a very special form, then that doesn't change Verdi goodness. So that's a weak form of chain homotopy invariance. And there's more. If a triangle is contractible, which means that its identity map is null homotopic. Yeah, here's a little example. Being split implies being contractible, but the converse is not true. Well, Neeman observed that if you're mapping from a contractible triangle or into a contractible triangle, then this map is automatically Verdi good, which you can think of as a weak form of chain homotopy invariance. Because if we had chain homotopy invariance, then we would conclude that automatically. But in this case, it's true. All right, let's look at some more examples. This map, another example of Neeman, is always middling good. You can just actually write down the 4x4 diagram that extends it. And it's not always good. In fact, it's going to be good if and only if that third map W is a lightning flash. And that's not always the case. So if you want to produce some silly counterexamples, just make sure that there are no non-trivial lightning flashes. For instance, if there are no maps from the suspension of X into Z, but there are some non-zero maps W. So already that gives you an example that's not good, but is middling good. And the same trick works for Verdi goodness. We checked that Neeman's example also works for Verdi goodness. The same conclusions are true. All right, so what's going on here? We've got, those two notions. Middling good, oh, right, and middling goodness is not chain homotopy invariant, because if you go back to the previous example, it was chain homotopic to this simpler map 0,0W. Right, what was the chain homotopy? You just stick in the identity right here. You can remove that, and that's going to get rid of the U and get rid of the V. So turns both into zeros. But we saw that this one is not always middling good. So there are some strange phenomena going on, and the goal is really to sort out what's going on. So we've got those two notions of goodness and Verdi goodness. They both imply middling goodness. They're both strictly stronger than middling goodness. And they seem to be related, at least in many cases. They seem to be even equivalent. And in fact, so far, we haven't found an example that's one but not the other. So those are the questions we want to look at, or we would love to answer in full generality. Are they equivalent? Are the two notions equivalent? Or at least is one stronger than the other? Does one imply the other? Based on the examples we have so far in the partial results, it seems like goodness would imply Verdi goodness, but even that is not completely obvious. And is Verdi goodness invariant under chain homotopy? There's some evidence for that, but is it always the case? Or at least if a map is null homotopic, does it have to be Verdi good? That would be a weaker form of chain homotopy invariance, but a useful one nonetheless. And same thing with rotations. I mentioned this asymmetry in the construction that factors the third map H in a specific way. So the definition is not rotationally symmetric. You can't just factor the second map G or the first map F. So it's not obvious that the definition is invariant under rotation. But let me give you some results in those directions. Now, first of all, we're used to this strategy of factoring a complicated map into simpler steps and then tackling the simpler steps individually. That's not going to work here. It's completely useless because it turns out that every map of triangles can be factored as two steps, so a composite of two maps of triangles, both of which are good and Verdi good. So yeah, it's not going to be useful to factor your map into simpler steps. Right, so those conditions, those properties are not closed under composition. Well, let's look at some known cases. If you look at a map of triangles where the first two components are monomorphisms and in a triangulated category that's automatically split, then the two notions do agree. Good is the same as Verdi good. And likewise for epimorphisms. And if the first map happens to be an identity, then Neeman observed that good implies Verdi good. Not phrased in those words, but that's what his argument showed. And in fact, just those maps 1GH are quite interesting. There's a lot going on here. So I'll devote more time to those maps later. They're related to homotopy Cartesian squares. And if you have two components and a zero, then you can almost characterize what's going on. Well, first of all, if you want a null homotope such a map, you can always do that with a simpler null homotopy that's just in one of the squares. And then using that, we show that such a map, FG0, is good if and only if it's null homotopic. And well, that is rotationally symmetric, so you can put the zero wherever you want. And if the zero is elsewhere, then that's also equivalent to Verdi goodness. And under some very mild assumption, if you have a little bit more structure, then good implies Verdi good for those maps. A three triangulated enhancement. That's in the sense of multi-neotis, of higher triangulated structures, but that's satisfied by the homotopy category of any stable infinity category in particular, so that it's a very mild condition. So that's some evidence that at least in some cases good seems to be stronger, but we don't know that for a fact if that's always the case. And here's a fun little corollary. Well, let's say you're starting with a square and you're trying to find a lift. As homotopy theorists, that's something we look at all the time, trying to lift in a square. Well, you can extend the rows to cofiber sequences, so exact triangles. And then this previous slide was saying that there's going to be a lift if and only if 0 is a good fill-in in that third row. But 0 being a fill-in is not sufficient. If you want this a small counterexample, you can look at this diagram in the derived category of abelian groups. 0 is a fill-in, but there is no lift. So you really need 0 to be a good fill-in. All right. Now, as promised, let's go back to those maps of the form 1GH and their relationship to homotopy Cartesian squares. And I think we'll see some of the subtleties that arise in this whole business. So first, what is a homotopy Cartesian square? Well, it's a square that such that there is an exact triangle of this form that I like to call a Meyer-Vietoris exact triangle, because that's the usual Meyer-Vietoris triangle from topology. And this map here, del, is called the differential. But the fact that del was not prescribed to begin with is the subtlety here. So just being homotopy Cartesian means that there exists a del making that true. It's not part of the data. Right. And Neeman observed that, okay, if you start with a homotopy Cartesian square with a certain differential, then in fact you can extend it to a map of triangles of the form 1GH, where this prescribed differential del factors as, well, this map, W prime, then go up, and then the suspension of U. Right. So if someone handed you the differential, you can embed your square into this diagram with this specific factorization. Now you might wonder, oh, and yeah, it gets better. You get to prescribe the top row or the bottom row. So your favorite exact triangle that extends, say, U prime, you can choose that as your bottom row. But we'll see in some examples that you can't prescribe both. That's the issue. Now, what's the precise relationship between good maps of the form 1GH and homotopy Cartesian square? Can we make that more precise? Why, yes, we can. For that, I need a bit of terminology. So allow me to introduce this terminology that goes back to work of Vaknin. If I have a candidate triangle, by which I mean that the twofold composites are 0 and nothing else, well, maybe you can make it exact by changing one of the maps. If you replace, let's say, the map U, and you can make it exact, then, well, we say that U is replaceable. And maybe you prefer replacing V or W. Well, the definition extends similarly. And if it turns out that you can replace any of the three maps, so all three, then we say that the candidate triangle is replaceably exact. It's very close to being exact. You can tweak any of the three maps to make it exact, but it might still fail to be exact. And in that paper of Vaknin, he studied a whole hierarchy of exactness conditions, where I think split was the strongest one, and then you've got distinguished, and then you've got those that are replaceably exact, that's a bit weaker, and then he has virtual, and yeah, so he has a whole hierarchy of exactness conditions. So for our purposes, just know that replaceably exact is slightly weaker than being a distinguished triangle. And now we can characterize those maps 1GH that are good. Start with a map 1GH like this. look at the associated Majorvier-Torres candidate triangle, then the map you started with is good if and only if the middle square is homotopy Cartesian with the differential you would expect, namely this composite of going right and up and right again. In other words, the Majorvier-Torres triangle is exact. If you just care about homotopy Cartesianness of the middle square, then that's equivalent to the Majorvier-Torres candidate triangle being replaceably exact. If you don't care about a specific differential, then that corresponds to being allowed to tweak this triangle a little bit, just one spot at a time. And finally, the map is Verdi good if and only if it extends to an octahedron, in the sense that you can write down an octahedron with those two rows at the top. That's the usual flat picture for an octahedron like we had before, with the missing pieces here, like a T shape. Right, that's what's going on with the maps 1GH. And already you see this subtlety appearing, this weaker version of exactness, the replaceable exactness. And this is also related to a paper of Kanonako and Matthias Kunsa, where they were looking for conditions guaranteeing that if a square fits into a map 1GH, then it's forced to be homotopy Cartesian. So it's a related but different question. And they found some sufficient conditions where that is the case. Right, using those facts about good maps of the form 1GH, we get this pasting lemma. If you start with two homotopy Cartesian squares and you paste them, the big rectangle is still homotopy Cartesian. And maybe the naive approach would be to say, well, okay, I can just extend each of the two squares to one of those maps 1GH and just hope that the factorization I see this way, right, and then up and right again gives me a differential for this Majorvier-Torres triangle. But no, that doesn't work in general. So you do need to work harder to prove the pasting lemma. And in fact, I'll provide some examples showing the failure of the naive approach. Oh, it gets better. If someone hands you differentials for the upper square and the lower square, then you can find a differential for the pasting that's as compatible as it could be with those given differentials, meaning that those equations hold. So yeah, that's the best you could hope for. And Vaknin's paper was proving, yeah, a slightly weaker exactness condition. So this strengthens his result. All right, now let's jump into those examples. I promised some examples in stable module categories. In fact, in a single stable module category, that of F2C4. C4 is the cyclic group of order 4 with generator, let's call it G. And then I take the group algebra F2C4, which is just a truncated polynomial algebra over F2 of this form, where X is not the original generator, but the original generator minus 1, right? Its fourth power is now 0. And we'll work in stable modules over this group algebra. So I need to tell you how to denote the morphisms in there. And well, because we get rid of free summands, it's really morphisms of that form that are important. And I'll denote by mu sub r, just multiplication by r. For example, multiplication by x sends 1 to x and x to x squared. So this one is well defined. Right, so this notation is used only when it's defined. All right, with that notation at our disposal, let's look at a few examples in stable module over F2C4. All right, let's start with a warm-up, gentle example. Here's a map of triangles, and it's exactly the one you would expect if everything goes nicely. It's exactly the map you would hope for, and it's good and Verdi good, no problem there. All right, now let's play a game. I'm going to show you a very similar picture, but there will be one subtle difference. Can you spot it? Give you a few seconds. Can you spot the difference between those two pictures?
Over the right-hand corner.
Yeah, that's right. The right-hand corner, right there. There it is, right here. So right there, we've got this mu1, which is, what is mu1? You restrict to the second summand and map into the first summand. Yeah, it's this quotient map from r mod x squared into r mod x. That's just modding out x. That's what it does in R modules. And it's not a quotient map anymore in stable modules, of course. It's an more interesting map, and it just messes up this map of triangles, whereas you had a 0 here. But note that the middle square is the same, so it's still homotopy Cartesian, but it sits in this map of the form 1GH that is not good. And that illustrates the difference.
Is in the upper row, the composite of the second and the third map, is that really 0?
Oh, let's see. So this one here, yeah, let's see what's going on here. So when you restrict to the first summand, that's already 0, so that's fine. If you look at the second summand, if you restrict to the second summand, you get, okay, so you mod out x. Yeah, it is 0, because we modded out x, and then we multiply by x. Wait, is that what's going on? Let's see.
I mean, it looked like one.
It factors via projective. It factors via R modulo x4.
Oh, yeah, that's right. It factors through R modulo x4. Yeah. Yeah, that's right. It is stably null. It's not the, it's not the 0 map in modules, but it is stably null. Yep.
Thanks.
Yeah, thank you. Right. And right, so already we see the subtlety distinguishing between those good maps 1GH and those where the middle square is just homotopy Cartesian. And in fact, this weird phenomenon can be made even worse. We can spread out the weirdness over 2 steps. I don't expect you to absorb this whole diagram in the next 2 seconds, but it's just a jazzed up version of the previous example where you make the weirdness happen in 2 steps. And the upshot is that the top row in that example is good. The bottom row is good, but their composite is not good for the same reason as the previous example. And that shows in particular that good maps of the form 1GH don't compose. However, if you think back to the pasting lemma, we're guaranteed that this big rectangle in the middle is homotopy Cartesian. And the issue is that, yeah, its differential is not the one you would expect from this diagram. It's not the one given by just going to the right and then the suspension of this map here. So in other words, the Meyer-Vietoris triangle is replaceably exact. That's guaranteed by the pasting lemma, but it's not exact. So yeah, you run into those kinds of subtleties in that business. And those examples were small enough that we could compute them by hand. However, we're thinking that if we're going to solve some of the remaining open questions and look for those weird counterexamples, yeah, hand computations will hit a limit pretty quickly. So we're thinking that we should try some computer-assisted calculations. And there's this paper of Matthias Kunsa where he produced some weird counterexample in stable module categories using Magma, so using some computer-assisted calculations. And so some of you in the room are experts in stable module categories. So I would love to hear if you're familiar with maybe more recent developments in computer algebra and some useful computational tools for stable module categories. I would love to hear about that. I haven't really looked into that or contacted Matthias Kunsa. Maybe I should. And maybe another source of weird phenomena would be to look at triangulated categories that are not the homotopy category of some stable model category. So yeah, those weird counterexamples in the first scenario at least show that the weirdness is not because of the lack of models, right? Stable module categories are as nice as it gets. They're homotopy categories of nice stable model categories. So that's not the issue. But perhaps if you look at those triangular categories that are not homotopy categories of stable model categories, maybe you'll find some of those strange counterexamples. Referring to some examples by Moreau, Schwede, Strickland, and then a follow-up paper by Berg, Yasso, Taule. And yeah, their paper was also generalizing to n-angulated categories, those that appear in representation theory. And that's another related train of thought. Does this story of good morphisms and Verdi good and middling good also generalize to n-angulated categories? Those are, it's totally different from what I talked about with the enhancements a la Maltziniotis. It's a completely different direction. It's not giving more structure, it's giving longer triangles. So those n-angulated categories are those appearing in representation theory. I think in tilting theory, if I remember correctly, some of you know better than I do. And so Marius Taule and his student Sebastian Martensen have been working on that. So trying to see what happens with good morphisms and Verdi good morphisms in angulated categories. Thank you for your attention.
Thank you, Martin. Can we all unmute ourselves and give the speaker a round of applause? Okay, if you have any questions for Martin, please ask them now. You can unmute yourself or put them in the chat.
So perhaps, so thank you for the talk. I noticed that so the first part was about the Adam spectral sequence. The second part was about the good and Verdi good and other type of morphisms of triangles. And at the juncture, you explained why you cared about the second for the first, but could you repeat that or give some applications of
right, that was a break there in the story. So let me go back to that point. Right, the reason we started wondering about that was because we're working on the triangulated Adam spectral sequence, and then, well, you start with your objects and then you resolve them. So you build this Adams resolution. But now when I say Adams tower, it's just the top part of the Adams resolution, right? So I forget these intermediate steps. Just take the top row here. That's an Adams tower. And right, we ran into this issue where you need to look at maps induced on cofibers. And if you happen to be working in some nice model category, you don't really run into this problem because you have honest inclusions and honest quotients of sub-objects, and then you just take the induced map out of the quotient. So that doesn't cause problems. But if you just have the triangulated structure at your disposal, then those are just cofiber fill-ins. And we needed those to satisfy the kinds of compatibility conditions that you would see if indeed you just had some sub-objects and some quotient maps. Right, if you play around with those indices, the maps should be compatible and satisfy some equations. So that's why we wanted to make those choices in a way that's as structured as possible. Does it clarify?
So is the goal to show that the extension or the lift, whatever, is unique up to homotopy instead of being unique up to something where you have differentials on both sides, where you have homotopies on both. There's this work of Bondarco, right, for weight structures, which is reminiscent of that.
Right, and right. So Bondarco did
blending in the homotopy category of the injective objects. He would have to mod out maps which have homotopies in a weaker sense, that you say you allow the homotopy to change in every degree on the left and on the right. You're not using the same homotopy in degree n and in degree n-1. You're changing at every degree.
Right.
And so this is an additive quotient of the homotopy category in the sense of complexes up to homotopy.
Yeah, that's a very interesting remark. So I've looked a little bit at Bondarco's work, and much of his work uses extra structure, typically a T structure or something along those lines. But I think you're right that
weight structure.
Right, weight structures, yeah, in several of his papers, that's right. But I think you're right that you could also just say, well, if you get extra indeterminacy, just get rid of it, just force it to become zero by quotienting out. I haven't really thought about that approach, but I think it's related.
So just stepping back, what do you get? What new result do you get on that topic from the second topic, from the work on?
Well, right. The goal here was to get the Moss pairing in full generality. In the meantime, there's this really interesting paper of was it Belmont and Kong, I think, and maybe other co-authors, about the Moss pairing in a setup where you have a monoidal structure, and it turns out that you can either compose maps or tensor them together. Like in good old-fashioned homotopy theory, the stable homotopy ring can be obtained by composing maps between spheres or just smashing them together. So they have a paper about the Moss pairing in that situation.
I'm not sure you should rely. I think they're ignoring some technical issues in that paper.
Could be. I haven't read it line for line, but at least just from
I'm pretty sure there are technical issues remaining.
Right. And one thing is that they do assume a stable model category in the background. So they were aiming for the practical applications to computational homotopy theory, and I think that's the right thing to do in that context. So there still remains to produce the Moss pairing when you don't have the monoidal structure and when you just have a triangulated structure. This is, it's not yet completed, but yeah, so we're hoping to get this triangulated Moss pairing using this technology. That was the original motivation. Still in progress.
They are ignoring technical issues is my new favorite euphemism for a wrong paper.
Well, I'm pretty sure there's at least a gap. I mean, but it's not. I don't think it has been refereed or accepted by a journal yet.
It's in preprint form, and it looks very promising, at least from what I've looked at. So.
Thank you for that.
Yeah.
I mean, so in a way, what you're looking at, if you had a cofiber sequence, on this slide, you have the Adams tower for X. And if you had a cofiber sequence X to Y to Z and then back to sigma X again, maybe then you could sort of try to compare the Adams towers for X, for Y, for Z. And
you would expect,
try to compare for
some kind.
So you might hope that there's some connection between the connecting homomorphism, say from Z back to sigma X, and some interaction with differentials in the various Adams spectral sequences.
I think that's right. So certainly the you want this Adams spectral sequence to be natural in both objects, and it is. That much is fine. But what you said is, it's something a bit stronger, and I think it is also true. I don't know.
Well, I don't
remember if it's automatic from the construction. I think you have to check something there for this compatibility that you just mentioned.
Yeah. So if you have the 4x4 diagram someplace. There's something I call the push-pull lemma, which I was wondering about how it interacts with your three goodness properties. Could you show a 4x4? Could you show the 4x4 lemma someplace?
Yeah, this 4x4.
Yeah, for example. So if you start with something in Z double prime.
Yep.
So I'm thinking of the situation here where let's see, okay, so you had X, Y, Z on top. So we could think of a cofiber sequence of spectra X, Y, Z, and then vertically you have some sort of Adams resolutions, parts of the Adams.
Yep.
The Adams resolutions would involve triangles where you might focus on just a few of them here.
Yeah, exactly. Maybe those are sub-objects and those are
and then there could be and you could have then if you start in Z double prime, if you have something in Z double prime that goes to 0 when you map down and maps to 0 if it goes to the right. So that could correspond to some appropriate cycle in the spectral sequence. So if you're in Z double prime and it goes 0, both going down and to the right, it means on the one hand, you can lift it through H prime, map across by double prime and lift to sigma X. So you could pull and then push to the right and pull back up. I'm just saying there's one way to get to sigma X by saying you lift over H prime, push over W prime and lift over sigma F.
Right.
Or you could go the other way, start going back to Z double prime, you could lift over V double prime, push to G double prime, and lift to sigma X.
Yep.
So there are two different ways of producing elements in sigma x. And there are a number of arguments in the literature that say that these have to be the same or have the opposite sign under variously specified hypotheses.
Right.
And I think your examples of things that are middling good but not good show that it's not always true that these two things are going to be the same even up to sign.
That's a great point.
I think it's true that if this diagram arises, if there's a compatible symmetric monoidal structure, and if it arises by taking the tensor product of two cofiber sequences, then I think it's always true that the two ways of pulling and pushing and pulling.
Right. I think that statement might be in one of May's papers.
Yeah, you can deduce it in adjoint form. It's kind of, I haven't actually found it explicitly there, but that is in the literature. But I'm curious about what are the conditions under which this kind of a pull-push-pull condition holds.
Oh, that's a great question. Dan, do you have any idea if that's true? I feel like it's not automatic.
Well, all I can say is that our previous paper, the one on the total brackets, exactly that issue came up.
Yeah.
I mean, I forget exactly what we were able to say about it, but I agree that that's a subtle point that's easy to miss. That
there are cases where people say that just because you have kind of a lattice with exact sequences horizontally and vertically, then those two constructions have to be equal or up to sign.
Yeah, no, I wouldn't believe that.
That's not true. So I'm sort of curious about what makes it work.
I definitely remember thinking about that issue.
I mean,
yeah,
so Heinz Miller has a lemma in his paper comparing the Adams and Adams-Novikov spectral sequences, and he basically pushed, one of the directions here corresponds to an Adams resolution, and the other direction to an Adams-Novikov resolution, and he's making this kind of comparison to compare differentials in the two spectral sequences.
Right.
And in the 1980 version of that paper, the proof again requires a little adjustment. But I think that may be why he sort of returned to Verdier's paper and he sort of says that his other characterization that you also cited is supposed to resolve that issue here, and I never quite understood.
Could be. I do believe that you need more coherence than just the 4x4. That so certainly sounds true.
So it could be that Verdier goodness is. If I think Heinz Miller is sort of implying that Verdier's argument gives this. So if this comes from a Verdier good fill-in, maybe that's enough.
Maybe that's enough because So I mentioned those two notions, and I said that we're wondering if they're the same, but they have different benefits. Verdi goodness is nice because it comes with this package of extra equations. Whereas goodness is nice because by nature it's closed under rotation and chain homotopy invariance. So so they have completely different features, and we'd like to get the best of both worlds. But in this case, I think you want some extra equations. So Verdi goodness sounds like what would be helpful.
It could
that's
be
a great question. Yeah,
it could be that this pull push pull going one way or pull push pull going the other way amounts to some of the commutative hexagons that Miller points out.
That's a great point. I'll make a note
I should
of
say,
that.
I mean, there is some indeterminacy. Pull push pull will give you indeterminacy, but it's the same indeterminacy in both directions. In both cases, it's the maps, I think, from the double D suspension of Z double prime into. Well, you could chase, but I mean, you can figure out that you're really comparing two subsets with exactly the same indeterminacy. So it's kind of makes sense to ask whether they're equal or not.
Right. No, that's a great point. I'll make a note of that. Thank you.
Are there any more questions? And thanks, John and Paul. I wanted to, well, it's a silly remark / question. So when you said, Martin, that there is some work to be done on, what was it, computer calculations in the stable module category?
Yeah, it's something I would love to know more about, because those little examples in stable modules
there was
over F2C4.
Yeah, there was a reference. There was a reference there. I'm trying to.
Yeah, that was Matthias Kunsa. His weird example was the non-isomorphic octahedra over the same base. The base being just the two maps you start with, and they're composite. And then you've got the octahedron comparing the cofiber sequence for the first map and the second map, and they're composite. And he produced an example of two non-isomorphic octahedra over the same base. And he did that in magma in some stable module categories. And
I was going to ask what
so
package. Okay. In magma.
Right. If some people here in the room happen to know some computer algebra that would be helpful, I would love to hear about that. Just email me or something.
Okay. Okay. Do we have any more questions? If not, let's thank Martin again.
Thank you.
So next week we have Ina and Tova Eisenberg from Ben Gurion, and the week after that we have Jordan Williamson. I think the week after that Jesper Brodal, and the week after Sergey Brook. So yeah, thank you all for coming, and yeah, hope to see you soon. Bye bye.